Imagine for a moment you're on a video call, maybe with family overseas, or you're just streaming your favorite show, I don't know, while you're stuck in an airport or walking down a busy street. Your device, right? Your phone, your laptop, whatever it is, it's just pulling in and pushing out this constant stream of information. And, well, it just works, most of the time anyway. But have you ever really stopped to think about the incredibly complex dance happening behind the scenes, the invisible stuff that makes it all possible? Like, how does your phone or your Wi-Fi router, how does it actually know what kind of signal it's receiving? Is it voice? Is it video? Is it just data? Because each one might be encoded totally differently, almost like different radio dialects.
Exactly, and that's the core of it. That fundamental ability, identifying the dialect of a radio signal without being told up front, that's where Automatic Modulation Classification, or AMC, comes in.
AMC.
It's kind of the unsung hero in all this. It lets these intelligent receivers make sense of, well, the absolute chaos of radio waves all around us.
Right, the intelligent receivers bit sounds key.
Oh, absolutely. And that concept is vital because AMC isn't just some, technical curiosity for engineers. It's really the foundational brain that allows these devices to actively understand the radio environment. They don't just sit there passively. They listen, understand, and then they adjust to what's happening.
So they're actively thinking, in a way.
You could say that. It's truly a fundamental capability for these intelligent receivers. Yeah. They really are the unsung heroes of future wireless communication. They're powering these incredibly advanced concepts like cognitive radio and adaptive modulation. Without AMC, these systems just wouldn't be able to dynamically adjust or optimize their performance or even figure out what kind of information they're actually getting.
And that brings us neatly to our mission for this deep dive. You, our listener, sent us this really cutting-edge research paper. It digs into a novel AI approach for this very thing, for AMC. So, our goal today: break down this pretty complex topic into insights you can actually use. We'll focus on the innovation in the paper, how well it performs, and maybe most importantly, what it means for, the future of how we all communicate.
Sounds good.
Okay, so let's jump right into it. Let's unpack this invisible challenge of decoding radio signals. Why is it so hard?
Well, when we talk about these intelligent receivers, AMC is absolutely pivotal. It's not just nice to have, it's essential for the next generation of wireless tech. Think about a world where devices don't just passively receive, but they can actively listen, understand, and then react to the constantly changing radio environment around them.
That sounds like a big deal for a lot of different areas.
It really is. It's critical for an incredibly wide range of applications, everything from, vital military operations to everyday commercial uses. On the military side, for instance, think about intelligence gathering or identifying unknown signals, maybe adversarial ones, and deploying countermeasures in real time. That capability can literally be the difference between mission success and failure.
Okay, that makes sense for military use, but commercially, how does that translate to us? Our phones, our Wi-Fi?
Commercially, it's just as transformative, really. It's about making sure we use the available radio spectrum as efficiently as possible. That's huge, especially in crowded places like cities or big events. It also means more robust communication, keeping your connection stable and clear, even when there's a lot of interference or noise.
Better signals in crowded stadiums, maybe.
Potentially, yes. But more profoundly, it lets devices truly understand the radio spectrum and adapt instantly. Instead of being rigidly programmed for every possible scenario, an intelligent receiver with AMC can just identify a signal, figure out its characteristics, and then reconfigure itself to receive it optimally or even transmit back in the best way for that specific environment. That adaptability, that's the cornerstone of future smart networks.
Okay, here's where it gets really interesting for me. Why is this such a tough nut to crack? Why isn't recognizing a radio signal, as simple as your phone recognizing your face?
That's a great question. The core problem is what we call blind modulation recognition. Imagine trying to read a secret message, but you don't know the language, you don't know the alphabet, you don't even know if it's written forwards or backwards.
Okay, yeah, that sounds impossible.
Your phone, or any receiver, faces a pretty familiar challenge. It has basically zero prior knowledge about the signal coming in. It doesn't know the data, it doesn't know the specific modulation scheme used, it doesn't even know many of the basic parameters of the signal itself.
So it's completely in the dark.
Exactly. It's flying blind.
Yeah.
And there's so many unknown parameters that just make it incredibly difficult. For instance, you have things called phase offsets.
Right.
This means the signal starting point in its wave cycle might be randomly shifted. Think of a perfect wave starting at 0. A phase offset means it might start halfway through or somewhere else entirely.
Right.
Then you've got signal power variations. The strength of the incoming signal can fluctuate wildly. 1 second it's strong, the next it's almost gone. That adds a huge layer of unpredictability.
And it's not just the signal itself, right? You mentioned the environment plays a big role.
Precisely. You also have imprecise timing information. The receiver isn't perfectly synchronized with the sender. Even a tiny misalignment in timing can completely scramble the data. And then there are carrier frequency shifts, where the signal might be slightly off its intended frequency, like trying to tune an old radio where the station keeps drifting a bit. And it gets even worse in the real world. It's not a clean signal in a lab. You have constantly changing channels. Picture your signal bouncing off buildings, trees, cars, people.
That sounds like pure chaos, like listening to someone talk in a really echoey room.
That's a very good analogy. It leads to something called multipath fading. The signal arrives at the receiver via multiple paths, often at slightly different times and with different strength. Just like those echoes, right? Each echo is a bit out of sync, creating interference, degrading the signal, sometimes really badly.
So that's why sometimes your call drops or your video buffers.
That can definitely be a major factor, yes. The signal gets all muddled because it's bouncing around. An intelligent receiver has to somehow filter out all that confusion and reconstruct the original signal.
And you mentioned this blind challenge is particularly tough for software-defined radios, SDRs. Why is that, and how do these intelligent receivers help?
Right. So traditional commercial radio systems often need extra info, like a prearranged handshake between the sender and receiver, just to know how to reconfigure themselves for a specific modulation type. This creates overhead. It's like needing detailed instructions every single time you encounter a new signal type. Consumes time, consumes resources.
Less efficient.
Massively less efficient, especially in dynamic situations. Intelligent receivers, though, they bypass this. By using these blind techniques, they can just autonomously identify and adapt to the incoming signal without any prior instruction. It's a huge leap in efficiency and reduces that unnecessary overhead. It really paves the way for truly adaptive, autonomous, wireless communication.
Okay, so given these huge challenges, how have people tried to solve this AMC problem over the years? You mentioned it's been an evolution.
Oh, absolutely. It's been a fascinating journey. Early efforts, they really focus on what you might call traditional methods. One key approach used likelihood-based or LB techniques. These were pretty common for simpler linear digital modulations.
How did those work, roughly?
Essentially, they'd calculate the probability, the likelihood, that a received signal belonged to a certain known modulation type based on statistical models. It was kind of like trying to fit puzzle pieces based on expected shapes. Mathematically sound, but they often really struggled with real-world noise and all that interference we talked about.
Okay, so probability-based. And then I assume machine learning started creeping in.
Exactly. As computing power grew, researchers started exploring things like fuzzy logic for classification, trying to handle the inherent ambiguity, and then more standard machine learning techniques came along. For example, extracting statistical features from signal amplitude, frequency, phase characteristics, and feeding those into algorithms like support vector machines, SVM.
SVMs, right? I've heard of those.
Yeah, that are powerful classifiers. One interesting SVM approach used the spectral correlation of signals as a key feature, basically how different frequency components relate to each other over time. That specific method could classify 6 different digital schemes: BPSK, QPSK, 2FSK, MSK, 8PSK, and 4PSK. So a definite step up, but still, it had limitations.
And the big question, as always, how well did these ML approaches actually perform? Especially when things got noisy.
That's the critical point. That SVM model, for instance, it achieved about 77% accuracy at a strong 20 dB signal-to-noise ratio, or SNR, which is, pretty decent when the signal is much stronger than the noise.
But,
and this is the crucial part, its performance dropped significantly at lower SNRs. At 5 dB, which is much closer to a realistic noisy environment, accuracy fell to only 55%.
Ouch. That's not great if you're relying on it.
Not at all. Imagine trying to stream something important in a crowded place. 55% accuracy means buffering, dropped connections. It's just not reliable enough. This vulnerability to noise was a major bottleneck for these traditional and early ML methods. As the signal got weaker, or the environment noisier, their ability to tell the modulation types apart just plummeted.
Which perfectly sets the stage for the big shift to deep learning, or DL. Why did DL suddenly become so promising for this specific problem?
Deep learning really took off. because it fundamentally outperforms traditional ML in these kinds of complex pattern recognition tasks. The key reason, as the paper puts it, lies in its exceptional learning capabilities and enhanced performance, especially with large, complex, messy data sets like radio signals.
How so? What's the fundamental difference?
Well, traditional methods often rely on experts to handcraft features, basically telling the algorithm exactly what patterns to look for. Deep learning models, on the other hand, can automatically learn intricate patterns and representations directly from the raw data itself. They discover hidden relationships without needing explicit instructions. That ability is a massive advantage in the noisy, unpredictable world of radio signals. It leads to much more robust and accurate classification.
Okay, so before we dive into the specific innovation in this paper, what did those early deep learning attempts look like? How did people first start applying these powerful tools to AMC?
Early on, it was mostly about using simpler convolutional neural networks, or CNNs. CNNs are really good at finding spatial patterns, kind of like how image recognition software spots edges or textures in a picture.
So applying image recognition ideas to radio waves?
In a sense, yes. Looking for patterns in the signal's representation. Some early models use maybe just two CNN layers followed by standard dense layers, and they could classify, say, 11 different modulation types. Others tweak this, maybe using amplitude and phase data as input instead of the raw IQ samples, seeing some small improvements. The core idea was feed the raw signal data in, let the network figure out the features itself.
But radio signals aren't static images. They evolve over time. I guess researchers quickly realized they needed to capture that temporal dimension too.
Precisely. That was the logical next step. You started seeing models that integrated memory, specifically using things like long short-term memory or LSTM networks. LSTMs are a type of recurrent neural network, really good at processing sequences and remembering information over time. Perfect for the time series nature of radio signal.
So combining the spatial pattern finding of CNNs with the time sequence understanding of LSTMs.
Exactly. Hybrid architecture started popping up. Some integrated residual blocks or inception structures with LSTM, trying to capture both spatial and temporal features more effectively. Getting the best of both worlds, right? The CNN extracts features, the LSTM understands the sequence. Then you saw the rise of even more complex hybrid dual-stream models. One key paper, referenced as 13 in the source, used a CNN LSTM dual-stream setup. It processed spatial and temporal information separately and then combined them. That really set the stage for the kind of approach we're looking at today.
Okay, so we've gone from basic probability through early machine learning to increasingly sophisticated deep learning hybrids. But there's this practical challenge you mentioned earlier, something the paper really emphasizes. Given how dynamic radio environments are, these AMC models need constant retraining. What does that mean for how they need to be designed? It can't just be about accuracy, right?
You've hit on a crucial point. This raises an important question that sometimes gets lost when everyone's just chasing that extra percent of accuracy. If these models need frequent retraining, maybe even hourly in some applications, then efficiency becomes absolutely paramount.
You just can't wait days for a model to relearn.
Exactly. A model that takes hours or days to retrain is basically useless for real-time, mission-critical stuff. So minimizing training time and complexity isn't just a nice to have, it's critical, especially, as the paper notes, for the next generation of wireless, which is mostly digital modulation anyway. The goal isn't just accuracy, it's accuracy plus speed, low computational cost, and the ability to adapt fast. That's the real balancing act, and that's what this paper tackles head on.
Okay, so what does this all mean for our deep dive today? This paper introduces something genuinely new, what they call a novel hybrid dual-stream structure. It sounds like a really clever mix of technologies aimed at solving both the accuracy and that critical efficiency problem.
Indeed. The heart of their innovation is this hybrid dual-stream architecture. It combines CNNs, great for spatial features, as we said, with gated recurrent units, GRUs, which handle the temporal side, and then it adds an attention mechanism on top to help focus on the important parts of the signal.
GRUs. We talked about LSTMs before. Why GRUs here?
Good question. We'll get into the specifics of GRU versus LSTM soon, but the key takeaway is that GRUs offer similar sequence handling power, but are generally simpler and faster to train. But back to the streams, the paper explicitly says the utilization of two streams yields more effective outcomes compared to employing single-stream configurations. It's not just about doubling the processing, it's about giving the model two different complementary views of the signal simultaneously.
It's seeing the signal from multiple angles, basically.
Exactly. It gives the model a richer, more diverse set of features to learn from.
That makes a lot of sense. So how are they feeding these two streams? What kind of data representations are going into each one?
They use two distinct but related representations, each feeding one stream. First, there's the in-phase quadrature, or IQ representation. This is pretty much the raw complex samples from the radio signal. You can think of it as two streams of numbers. The in-phase part, RIX, and the quadrature part, RQX. These are essentially the real and imaginary components of the complex signal wave.
Okay, the raw stuff. And the second type.
The second is amplitude phase, or AP. This is derived directly from the IQ data. Amplitude is calculated using the Pythagorean theorem, basically square root of I squared plus Q squared. It tells you the signal's instantaneous strength or loudness. Phase is calculated using the arctangent of Q over I. This describes the signal's angle or position in its cycle at that moment.
So one is...
provide different but equally vital perspectives. IQ often captures the linear aspects well, while AP might highlight nonlinear characteristics introduced by modulation. Using both ensures the model gets a really comprehensive picture.
And the data set they use to train and test this, you mentioned it's a standard one.
Yes, they used a well-known open-source data set called RML 2016 Tide 20B. It's kind of a benchmark in the field because it provides a huge collection of simulated radio signals under lots of different noise conditions. Really lets you test how robust a model is.
How big is it? What's in it?
It's pretty comprehensive. Each signal example has 128 samples in IQ format. For every modulation type and every signal-to-noise ratio level, there are 6,000 examples. And the SNR range is wide, from a very noisy, naggish 20 dB all the way up to a clear 18 dB in 2 dB steps. In total, it's about 1.2 million examples, all simulated at a 1 MHz sampling frequency. For this specific study, they focused on classifying 7 key digital modulation types: QAM16, CPFSK, 8PSK, QAM64, GFSK, BPSK, and QPSK. These cover a lot of ground in modern wireless systems.
Okay, 2 streams, 2 data types, IQ and AP, standard data set. Let's dig into what happens inside one of these streams. You said they're similar. What's the first step?
The first step in each stream is a convolutional neural network, or CNN, layer. Think of it as the initial pattern spotter, looking for those spatial features in the waveform representation. It automatically identifies recurring shapes or structures in that stream's data.
How does it do that?
Specifically, this first layer uses 256 filters, each size 2 by 3. These filters slide across the input data looking for specific, low-level patterns. Then there's an activation function called ReLU, Rectified Linear Unit.
ReLU, remind me quickly what that does.
Sure. ReLU is basically a switch. It introduces nonlinearity, letting the network learn complex stuff. If the input to a neuron is positive, ReLU lets it pass through. If it's negative, it blocks it. Simple, but very effective. After ReLU, there's a dropout layer set at 0.5.
Dropout.
Dropout is a regularization technique. It randomly turns off half the neurons during training for each training example. This stops the network from relying too much on any single neuron or feature, making it more robust and preventing overfitting, where it just memorizes the training data. Finally, they use zero padding to make sure the output size is consistent for the next layer. The output of this whole CNN block is a feature map, size 260 by 130, which then gets passed on.
Okay, so the CNN grabs the spatial patterns, the immediate shapes, but signals happen over time. What comes next to handle that sequence aspect?
That's where the GRU layer comes in. Now, connecting this back GRU, gated recurrent unit, is specifically chosen here because it's designed for sequential data, for capturing those time-related features. It's in the family of recurrent neural networks, great for data that unfolds over time, like speech or, well, radio signals.
You mentioned GRU versus LSTM earlier. Why GRU specifically here?
Right. If we connect this to the bigger picture, GRU is a really key choice. While it's similar to LSTM in handling time dependencies, remembering important stuff from earlier in the signal sequence, GRU has a simpler internal structure. Fewer gates, basically. This simplicity translates directly into faster training and less memory usage. Huge advantages when you're dealing with massive data sets and need rapid retraining, like we discussed.
Faster and leaner, but still powerful for sequences.
Exactly. This GRU layer has 50 memory units, or internal states, to track information over time. It also uses a 0.5 dropout rate for regularization. The output is a 50 by 130 feature map, a set of feature vectors capturing the temporal dynamics, which then goes to the attention layer.
Attention layer sounds like it's designed to, well, pay attention to the important parts.
That's precisely it. The attention layer's job is to help the model memorize a large sequence of data, but more crucially, to focus selectively on the most relevant parts of that sequence. In a noisy radio signal, not all parts are equally useful for classification. Some bits might be just noise. Others contain the key identifying patterns.
So it learns what to focus on.
Yes, the attention mechanism dynamically weighs different parts of the input sequence it gets from the GRU. It pays more attention to the features most likely to be useful for telling the modulation types apart and effectively remembers that critical information over longer stretches while downplaying the less important bits or noise. The output from this final layer in the stream is a very concise 50 by 1 feature vector. This represents the refined, attention-weighted essence of what that stream learned from its input data.
Okay, so we've got these two powerful streams. One processed the IQ data, the other the AP data. Each has gone through CNN, GRU, and attention, ending up with this compact 50 by 1 feature vector summarizing its findings. How do they actually combine these insights? This is the dual stream magic, right?
Right, this is where the two paths merge, and it's more clever than just sticking them together. After each stream produces its 50 by 1 feature vector, let's call them Estra1 from IQ and Estra2 from AP, they're combined using what's called an outer product operation.
Outer product. Sounds mathematical. What does it actually do?
Conceptually, think of it as multiplying every element from the first vector by every element from the second vector. It creates a grid, in this case a 50 by 50 matrix, where each entry represents the interaction between a specific feature learned by the IQ stream and a specific feature learned by the AP stream.
So it's not just adding the features, it's looking at how they relate to each other in pairs.
Exactly. It's like asking, what happens when we consider this specific temporal pattern from IQ together with this specific amplitude characteristic from AP? This allows a model to capture much more intricate, second-order relationships between the two different views of the signal. The paper highlights this perfectly. It facilitates the interaction of features from both streams in pairs, enhancing feature diversity. This richer feature set gives the final classifier a much deeper understanding to work with.
That makes sense, getting more than the sum of the parts. So after this outer product creates that rich 50 by 50 matrix, what are the final steps before the model makes its prediction? Like, okay, this looks like QAM16.
Almost there. That 50 by 50 matrix, packed with combined features, is then fed into a flattened layer. It does exactly what it sounds like. It takes that 2D grid of numbers and unravels it into a single long vector, just one straight line of all those features.
Okay, flattening it then.
That flattened vector, now containing all the integrated wisdom from both streams, goes into the final decision-making layer, a dense softmax layer. This is the classifier part of the network. It takes that long vector of combined features and calculates the probability that the input signal belongs to each of the 7 possible digital modulation schemes they're classifying. The modulation type with the highest calculated probability is the model's final output, its classification decision.
So the softmax layer essentially picks the winner based on all the evidence gathered by the streams.
Precisely. It maps the complex feature representation onto a simple probability distribution across the possible classes.
In the training process, how did they actually teach this complex network to make those good decisions? You need the right learning strategy.
Absolutely. The training strategy is key to making the architecture work well and efficiently. They use categorical cross-entropy error as their loss function. This is a standard choice for multi-class classification problems like this, and for good reason. As the paper notes, it helps achieve precise findings with little computation and quicker convergence.
So it measures how wrong the model is.
In essence, yes. It quantifies the difference between the probabilities the model predicts for each class and the actual true class, which is known during training. The goal of training is simply to adjust the model's internal parameters, its weights, to minimize this error, to make its predictions align better with the truth.
And how do they actually do that minimizing? What adjusts the parameters?
They use the Atom optimizer. Atom is a very popular and generally very effective optimization algorithm in deep learning. The paper highlights its advantages: fast computation times and requiring fewer tuning settings. This makes it efficient to work with.
How does Atom work conceptually?
Think of Atom as an intelligent way to navigate the error landscape. It looks at how the error changes as you tweak the model's parameters, that's the gradient, and uses that information, along with a memory of past adjustments, to decide how much and which direction to change the parameters next. It adaptively adjusts the learning rate for each parameter, often leading to faster convergence than simpler methods. During training, the network parameters are updated iteratively, batch by batch, using Atom to guide the adjustments. This continues until the error on a separate validation dataset, data the model hasn't trained on, stops improving, indicating the model has learned as much as it can without starting to overfit.
Okay, got it. So we've walked through the challenges, the history, and the intricate details of this dual-stream CNN-GRU-Attention network. Now, for the exciting part, the results, how did it actually perform? Did it live up to the promise?
Right, let's get down to the numbers. First, the setup. They used that RML 2016.10b dataset, splitting it 80% for training the model and 20% for testing how well it generalizes. Pretty standard practice.
And the training details.
They trained it in batches of 2024 examples, running 100 batches per epoch, one full pass through the training data. The Atom Optimizer used a learning rate of 0.001. And they did all this on some serious hardware, a Quadro RTX 6000 GPU with 24 gigs of memory. Shows the kind of power needed, but as we'll see, their model makes efficient use of it.
The paper has some really interesting graphs. One shows accuracy improving over training epochs. What did that reveal?
That graph is really important. It shows that the model does not suffer from overfitting. You see the training accuracy and the validation accuracy on the unseen test data climbing together and then leveling off. If it were overfitting, you'd see the training accuracy keep climbing while the validation accuracy stalled or even dropped.
So it learned general patterns, not just memorized the training examples.
Exactly. That's crucial for real-world performance. The graph also shows that the accuracy pretty much maxes out around 80 epochs. Training beyond that doesn't really help much, which also speaks to its training efficiency.
Now, this raises an important question. How well does it handle noise? That's the killer test, right? From really noisy signals to clean ones?
Absolutely. And this is where the model really shines. Looking at accuracy across different signal-to-noise ratios, it achieves over 75% accuracy across a really wide range, from negative 4 dB SNR up to 18 dB. Remember, negative 40 dB means the noise is significantly stronger than the signal.
That's impressive for such noisy conditions. What about when the signal is clearer?
When the signal gets better, say from 2 dB SNR up to 18 dB, the accuracy shoots past 96%. So in reasonably good conditions, it's almost perfect.
Wow. But how does that stack up against the previous best attempts, those other deep learning models you mentioned earlier?
That's the key comparison. The paper shows that when compared to other state-of-the-art DL models, like the standard CNN, CLDNN, and particularly that strong CNN LSTM models from reference 13, this proposed model exhibits significantly higher classification accuracy. And it does so across a very broad SNR range, from negative 16 dB all the way to 20 dB.
So it beats the previous champ.
Yes, and quite notably, the CNN LSTM model was already considered a big improvement over traditional methods. The fact that this new dual-stream approach surpasses it, especially across such a challenging range of noise levels, really highlights its superior design and learning capability. It's genuinely setting a new performance benchmark.
To get a finer-grained view, they often use a confusion matrix. What did that show? Can you remind us what it tells you?
Sure. A confusion matrix is basically a table. Rows are the actual modulation types, columns are what the model predicted. The diagonal shows correct classifications, how often QAM16 was predicted as QAM16, for example. Off-diagonal cells show mistakes, maybe QAM16 being misclassified as QPSK. Looking at the matrix for all SNRs gives you the big picture.
What's fascinating here is the performance at 0 dB SNR. That's signal equal to noise, right? A really tough spot.
Extremely tough. And at 0 dB SNR, the confusion matrix looks amazing. The diagonal elements are nearly 1. This means it's classifying correctly almost all the time, even when the signal is buried in noise. It shows incredible noise resilience.
Nearly perfect at 0 dB. That's remarkable.
It really is. The paper even mentions it achieves over 50% accuracy way down at number 6 dB SNR, where the noise power is 4 times the signal power. And at the clean end, 18 dB SNR, the diagonal elements are also practically perfect, confirming excellent performance when noise isn't an issue.
Okay, the accuracy is top-notch, especially in noise. That's huge. But let's circle back to that efficiency point, the need for fast retraining. You said this is where their model really shines.
Absolutely. This is, for me, the most compelling part for practical deployment. The paper includes a table 2, directly comparing their model to that strong CNN LSTM benchmark on efficiency metrics. The results are staggering.
Lay it on us. What are the key numbers?
Okay, first, trainable parameters. This measures model complexity, their proposed model. It's just 145,851 parameters. The CNN LSTM model, 11,149,528.
Whoa, that's almost 8 times less complex.
Exactly. It's a dramatically simpler, lighter model. But here's the kicker, accuracy. Their simpler model achieves higher accuracy, 68.23% versus 64.5% for the more complex CNN LSTM.
Wait, less complex and more accurate. That feels like it shouldn't happen.
It's the holy grail. It shows incredibly clever architectural design. It's not a trade-off. It's genuinely better on both fronts.
Okay, what about speed? Training time.
This is crucial for adaptability. Proposed model training time, 59 minutes. CNN LSTM training time, 219 minutes.
Nearly 4 times faster to train. That's a massive difference if you need to retrain frequently.
Huge difference. And then testing time, how fast it classifies a new signal once trained. Proposed model, 2.9 seconds. CNN LSTM, 8 seconds. Again, significantly faster in operation.
So the conclusion is pretty clear then.
Crystal clear. This proposed model doesn't just nudge the accuracy needle, it fundamentally improves efficiency. Higher accuracy, dramatically lower complexity, much faster training, and faster classification. It hits that sweet spot of performance and practicality that's absolutely vital for real-world wireless systems. It's a genuine breakthrough in efficient deep learning for this task.
So connecting this back to the real world, what are the big implications? Where could we see this kind of technology making a difference?
Well, if we connect this to the bigger picture, this combination, high accuracy, low complexity, fast computation, makes this model incredibly well-suited for real-time applications. Think about devices needing to adapt instantly to changing conditions.
Like what specifically?
Like detecting a new source of interference and switching frequencies on the fly, or rapidly identifying an unknown signal in a security context, or simply making cognitive radio and adaptive modulation truly practical. The efficiency allows it to operate seamlessly in practical scenarios where delays just aren't acceptable. It's the difference between reacting in milliseconds versus seconds.
This really is a shortcut to understanding where wireless tech is heading. Imagine devices that are just smarter, adapting instantly. It's not just about faster downloads, is it?
Not at all. It's a fundamental shift. It enables systems like cognitive radio, where radios can sense the environment and intelligently decide how and when to transmit, or adaptive modulation, automatically picking the best signal dialect for the current channel conditions to maximize reliability and speed, all without human intervention. This paper is a critical step towards truly autonomous, self-optimizing wireless networks. More resilient, more efficient, better performing comms for everything.
Okay, let's try and wrap this up. We've covered a novel dual-stream CNN-GRU model, boosted by attention. It grabs spatial and temporal features, nails high accuracy even in noise.
And, crucially, does it with way less complexity and much faster computation than previous top models, making it actually deployable.
Right. The efficiency is key.
Absolutely. Which leads to a final thought, maybe a provocative question. This raises an important question. As AI keeps getting better at optimizing these fundamental communication tasks, like modulation classification, pushing the boundaries of what devices can do on their own, what new frontiers might this unlock?
Beyond just faster data, you mean?
Far beyond just faster data. Could we see truly autonomous, self-optimizing networks? Networks that don't just react, but maybe predict interference before it happens? Or figure out the absolute optimal signal path in real time, dynamically routing traffic, created this ubiquitous, intelligent mesh that's constantly learning, constantly adapting all by itself.
A network that's actually intelligent,
Yeah.
a living entity almost.
Maybe. It's a future where the network itself becomes an active learning system. That's the kind of frontier these advancements might be opening up.
That's a pretty wild thought to end on. It really drives home how these seemingly niche technical advances could fundamentally reshape our connected world in ways we're only just starting to grasp. Fascinating stuff.